What's up, everybody? In this video, we're going to cover USACO's 2020 January contest at the bronze level. Problem number 2, photo shoot. Farmer John is lining up his N cows, where N is somewhere between 2 and 10 to the third. It's 1,000 cows, numbered 1 to N for a photo shoot. Farmer John initially planned for the ith cow from the left to be the cow numbered AI. Okay, so cows from the left, cow number 1, 2, 3, 4 from the left. What they're saying is that the cow expected in spot 1, spot 2, spot 3, spot 4 is going to be represented by AI. So A1, A2, A3, A4. What that means is that if A1 is equal to 6, that means that he expected cow 6 to be in spot 1. If A2 is equal to 4, that means he expects cow 4 to be in spot 2 and so forth. And he wrote down the permutation A1 through AN on a sheet of paper. So he wrote out the order that he planned the cows to be in. So maybe he wanted cow 6 first, and then cow 4, and then cow 3, and then cow 5, and then cow 1, and then cow 2, whatever. So he's written that down on a sheet of paper. Unfortunately, that paper was recently stolen by Farmer Naj. Luckily, it might still be possible for Farmer John to recover the permutation that he originally wrote down. Before the sheet was stolen, Bessie recorded the sequence B1, B2 up through B to the N minus 1 that satisfies BI equals AI plus 1 for each 1 less than or equal to I less than or equal to N. Let's pick that apart. That's a lot of symbols. So Bessie's sequence is represented by B1, B2, B3 up to Bn, similar to how Farmer John's was A1 through A4, whatever it was. Farmer John is writing down the original sequence. That's what the A's are for. The B sequence is N minus 1. There's one less number here than there were that Farmer John wrote down. And it satisfies the rule that for any number B, for B1, for example, it's equal to A1 plus A2. So B1 is equal to A1 plus A2. So these two numbers add together to make B1. B2 would be A2 plus A3. Let's go ahead and actually work through one of those because it's a little hard to follow. So let's say like I have 4 numbers. I'm going to do 2, 4, 1, and 3. And these are the A numbers. So A1, A2, A3, and A4. What Bessie has written down in the B sequence, there's one fewer number, and each number is equal to the A of the same index plus the A of the next index. So the first B number in this case would be 6, because that's 2 plus 4. The second number would be 5, which is 4 plus 1. And the third number would be 4, which is 1 plus 3. There, however, is no fourth number because B only goes up to N minus 1. So there's one fewer B number than A number. So what you're being tasked with doing is, given only B, 6, 5, and 4, try to determine what is A. So for example, if I've got a 6, that could be like a 2 and a 4. And then if I have a 4 here, and that could be a 4 and a 1. And if I have a 1 here, that could be a 3. And then that would satisfy this rule where 6 is 2 plus 4, 5 is 4 plus 1, and 4 is 1 plus 3. It's entirely possible there are other solutions to this, though. It'll explain that in a minute. So for example, what if I had a 4 starting here? If I had a 4, then I'd have 4 and 6. This would be 2. If I have 2 and then 5, then this would have to be 3. And if I have 3 and 4, then that would have to be 1. That still will satisfy the same B constraint, except this is a different result than what I originally started with. Okay, so we want to try and find the sequence that Farmer John's sequence A based on Bessie's sequence B. Based on Bessie's information, help Farmer John restore the lexicographically minimum, basically earliest, smallest number. If you were to alphabetize or treat it like a number, the lexicographically minimum number would be the smallest number. So for example, in the example I did above, I think I had 2, 4, 1, 3 was a potential solution, and then 4, 2, 3, 1 was a solution. This one is lexicographically smaller. It's the lexicographically minimum of the two because 2 is smaller than 4. If you were to put these numbers in order, this number comes first. So the minimum permutation A that could have produced B. A permutation X is lexicographically smaller than a permutation Y for some J, if for some J, Xi equals Yi for all I less than J and all Xj less than Yj. Let me see if I can pick that apart. So basically, for some J, Xi equals Yi for all I less than J and all Xj. In other words, the two permutations are identical up to a certain point at which X is smaller than Y. That's hard to pick apart. So we're looking for permutation X and permutation Y if for some J, X is equal to Yi for all I less than J, and X is J is, okay, so what they're saying is, for example, is if this was A, C versus, we're just gonna use letters A, D, then Xi is equal to Yi, these are equal, and these are equal for all I less than J, which means for any I position that is less than our J position, if J is over here, then everything before J is equal. And then once reaching J, the X, which is C in this case, is less than the D in this case, which is what Y is. And that only has to hold for all I less than J. So if J was 0, for example, if I have 1, 2, 3 versus 3, 2, 1, then the J would be here. This is the J, and then for all I less than J, there are no I less than J, but Xj in this case, which is 1, is less than Yj, which is 3. If on the other hand, I had 1, 2, 3 versus 1, 3, 2, then J would be this location right here. And then it is the case that for all I less than J, which means basically every digit before J, the values are equal up until J, at which point they're less. Another way to say that would be that there's some digit or some symbol where X is less than Y, and then everything to the left of it is equal, even if that's the first number of the sequence. So if I have 1, 2, 3 and 1, 3, 2, or sorry, 1, 2, 3 and 3, 2, 1, 3, 2, 1, then in this case, this is your J, and there are no I's less than that. That's a rather mechanical way to write this. You don't really have to totally understand this when you read this to be able to solve the problem, but we do run into things like this, so I'm taking a little bit of extra time to kind of pick this apart. These usually are very important to understand, so taking a little bit of time to figure out what they mean is good, and being able to interpret these is good. This one's a little tricky, but yeah, basically, just to kind of reread, an X is a smaller permutation than Y if for some J, for some digit, all I digits that are less than J are equal to each other, and then once you reach J, the Xj is less than the Yj. And again, that easy way to say that is it's like alphabetized, or the smaller number comes first. It is guaranteed that at least one such A exists. All right, so test cases 2 through 4 satisfy n less than 8. 5 through 10 satisfy no additional constraints. The large number of n doesn't really matter. I don't think there's any kind of an n squared or n factorial solution here. I think that this test 2 through 4 is just in case you weren't sure. So if you just set up like a for loop inside a for loop inside a for loop inside of a for loop or something like that. But there's a much easier solution that should run in a pretty simple time complexity. And the constraint of n less than or equal to 8. Again, I can't even think of an n factorial solution off the top of my head. But if you have an n factorial solution, you'll only get through the first 4 test cases. Input format comes from photo.in, so you'll have to make a file reader. The first line of input contains a single integer n. It's like this 5 right here. The second line contains n minus 1 space-separated integers b1 up through b of n minus 1. That's these numbers right here. So that's what Bessie wrote down, 4, 6, 7, 6, for example. The output format is written to file photo.out, a single line with n space-separated integers a1 through an. So we have to try and regenerate the original sequence. So for example, in this case, the sample output is 3, 1, 5, 2, and 4. Okay, and then it says A produces B. Oops, let's go ahead and just read over this last thing. It's always good to read everything. A produces B because 3 plus 1 is 4. 1 plus 5 is 6. That's the second row. 1 plus 5 is 6. That's the 6. 5 plus 2 is 7. That's the 7. And then 2 plus 4, the last pair, is 6. Okay, so 4, 6, 7, 6. 4, 6, 7, 6. If you haven't already, take a minute, go ahead and pause the video, take a minute to fiddle around with this with pencil paper, see if you can figure out kind of generally how to approach this. This is a pretty straightforward problem. There's only kind of so many ways that one could go about solving this. And if you play around with it with pencil paper, it should become pretty apparent. All right, so here's how this is gonna work. We wanna get the lexicographically, we wanna get the smallest number. I'm just gonna call it the smallest number. We wanna get the smallest number, if you were to consider it to be like a 5-digit number that would fit to producing this, this output. So pretty much once you establish what the first number is, everything that follows is going to be predetermined. So for example, if this first number was a 1, then for it and something else to add up to 4, the only possible second number would be 3, because there's no other number you can add 1 with to get a 4 other than 3. If we have 3 as our second number, then it and something has to add up to 6, which would be 3 again. Now, this is already a problem because we can't have cow 3 twice. So we know that we can't have 1 as the first number. 4, 6, 7, 6. So let's try 2. 2 is a pretty easy giveaway too, because if 2 is the first number and the second one has to add together with it to make 4, the second number has to be 2 as well. And we can't have cow 2 twice. If the third number is 3, then for 3 and some number to add up to 4, second number has to be 1. For 1 and that next number to add up to 6, that has to be a 5. For 5 and something to add up to 7, you've got to have a 2. And for 2 and something to add up to 6, that's got to be a 4. 3, 1, 5, 2, and 4. Those are all unique, which means that we've solved our problem. And that's the answer here. So let's pick this apart a little further and try to figure out how exactly we're going to do this from a coding standpoint. Basically, what's going to happen is let's start with a longer sequence. I'm going to do a sequence up to 8. We're going to do let's do 3, 7, 1, 8, 6, 4, 2, 5. Let's see, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, great. So I'm going to generate B out of this. So it's going to be 10, 8, 9, 8 and 6 is 14, 10, 6, and 7. Okay, so wanting to try to regenerate the original sequence here. So the first number you're going to try is 1. Now, one of the key things about this is we need to make sure we don't reuse any numbers. There's 2 really good ways to approach this. The first way is you could make a set. If you had a set of integers, then you can, every time you have a number, you can place it in the set. And every time you generate another number, you can check to see if it's already in the set. So if I put a 1 here, then I've got to have 1 and 10. So that's going to be 1 and something make 10, that'll be 9. So 9 goes in the set. I've got 9 and something has to make 8. Well, the only thing that would fit here is -1, and we can't have negative numbers. So that's already out. So first number cannot be a 1. Clear out the set, start over, start with 2. So 2 and 10, this would be an 8. 8 and 8 would be a 0. That's already a dead end again. So 2 would have been added to the set, 8 would have been added to the set. Let's roll back and let me see. I'm going to change the sequence of these numbers. Let's change the first number and the last number. If I were to have a 5 at the beginning and the 3 at the end, and that would change these numbers to, this would be a 5 and 7, and that'd be a 12. Okay. So just kind of looking at this, this can't be a 1 or a 2 or a 3 or a 4. It could be a 4. It could be a 4. Let's try 4. So I got 4 and 12. Yeah, see, the sequence just keeps giving me back 8s, and then that's canceling it out. I want to try and get one that goes all the way through. Let me pick a different number sequence. Let's do 3, 5, 2, 6, 4, 1. 1, 2, 3, 4, 5, 6. Okay. 5, 6, and 8. 5, 6, 7. 6, 8. 10, and 5. Okay. So if I were to plug a 1 in here, I'd have 1 go into my set. 1 and 8, this would have to be 7, so you got a 0 again. Let's try 2. 2 and 8. Okay, so 2 and 8, this would be a 6. 6 and 7, this would be a 1. 1 and 8, this would have to be a 7. 7 and 10, this would have to be a 3. 3 and 5, this would, I ran into 2 again. Okay, that's perfect. This is exactly what I need to do. Okay, thanks for waiting. So let's say like I picked 2 as my first number. 2 has to go in the set. I have to make sure that every number I pick has not already been used. So for 8, I'm going to have a 6. 6 is going to go into the set. For 6 to add up to 7, I'm going to need a 1. 1 is going to go into the set. For 8 and 1, I'm going to have a 7. 7 goes into the set. For 10, I have to have 7 and 3. So 3 is going to go in the set. And for 3 to add up to 5, I would have to have a 2. Now this 2 is already in the set. So because we checked that 2 is already in the set, that means we know we've used a 2 previously. Having it in the set will be a lot faster than going backward and checking all the numbers you've used before. If you go backward and check all the numbers you've used before, then for every number you attempt, you have to do a backtrack through everything. And you're going to have to do that for every single number you try. Now, because we've got potentially n starting digits, and then because every one of those checks of n checks is going to require looking through n numbers, if we do it this way with just a list, and if we didn't use a set, we would be in n cubed time. Since we are 10 to the third as a maximum of n, that would be 10 to the ninth. That would come very close to timing out. I haven't tested that to see if it times out, but that wouldn't be the way to approach it. We do have to use a set here. The other option, rather than using a set, would be to do an array of Booleans. So let's look at how that would work. And then we'll run through that one more time. Okay, so for an array of Booleans to work, basically what you would do is you would say, okay, I have n cows. So I'm gonna make n falses, essentially, for the numbers that I'm gonna generate. So this is false, 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 false. So as I pick out my numbers, I think I picked 2 for the first one. So I pick out 2, I go to index, this is 1 indexed because that's how the USACO problems always work. I'm gonna go to index 2, and I'm gonna change that to true, which means that's been used. So I have the 2 and the 8, that's gonna be a 6. Index 6 has to change from false to true. 6 and 7 is gonna give a 1. 1 is gonna change from false to true. 8 and 1 is gonna make a 7. There is no index 7 because we don't have 7 cows. So that actually right off the bat would have broken it. But let's pretend like we did have 7 cows. 7 would have to change to true. 7 and 10 would be 3. 3 would have to change to true. And then 3 and 5 would be 2. Index 2 is already set to true, which means that you can't use cow 2. So that would show that that doesn't work either. So those are your 2 approaches for keeping track of what cows you've used. One is to make a set. And if you're not familiar with sets, I have a video on sets that you can get to from my main page, or you can just do your own research. But a set allows you to uniquely add things to a container and to very quickly check whether or not those things are already in the container. The process of checking is very fast. The process of putting into the container is very fast, as opposed to like a list or a vector where you'd have to check every single item. The other option is to create a big Boolean array and then just switch them to true when the cows have been used. And I use this method quite a lot as well. But actually, this was good that this came up, as we not only need to make sure that all the numbers are unique, we also need to make sure that none of the numbers are too large. So if, for example, somehow this worked out and I didn't have duplication, maybe if this was like, I don't know, a different number or whatever, and this turned out to be okay. Even if we don't have any repetition of numbers, if we have a cow number that's outside of the realm of our n, which in this case is n equals 6, we already have gone out of bounds and we can't do that. So we do need to make sure that we don't go out of bounds. So let's recap one more time with the initial problem, and then I think you should be good to code this out. So for 676, first thing you want to do is you want to try the number 1. We need some sort of a container to keep track of whether or not things are unique. I'll use a set. So set, basically, again, you can add things to it and you can check if things are in it. So I put a 1 here. 1 goes into the set. 4 minus 1 is going to be 3. 3 goes into the set. 6 minus 3 is going to be 3. I'm just doing this one minus that one to get the next one. It's going to be 3. 3 is already in the set, which means cow 3 has been used, which means the first number cannot be 1. You can just run through these in a for loop. Next number to try is going to be 2. Here we go, clear that out. 2 goes into the set. 4 minus 2 is 2. 2 is already in the set, so the first number can't be 2. For loop's going to wrap back around and try 3. 3 is going to go into the set. 3 and 4 is 1. 1 goes into the set. 1 and 6 is 5. 5 goes into the set. 5 and 7. 7 minus 5 is 2. 2 is going to go into the set. 6 minus 2 is 4. 4 goes into the set. We've finished. So with 3, you always want to try the smallest number here. So these are going to count in order 1, 2, 3. And again, you can do that in a for loop. Test each one of those numbers. Try to go all the way across. Every time you add a number, add it to a set. Again, or you can use a Boolean array. Make sure it hasn't already been used. The numbers all have to be unique. Make sure none of the numbers go above n. We can't have any 6s in our solution if we've only got 5 cows. Make sure we don't have any 0 cows or negative number cows. We can't have negatives to fix this. We ran into that in one of my sample cases, which, by the way, that's another reason why you always want to come up with your own example cases. I just started doing random numbers, and I ran into several situations where I got numbers that were too large or were negatives or were zeros. This example doesn't really give you that. When you try out 1 and you try out 2, we didn't run into a situation where we hit negative numbers or zeros or numbers that are too large. And a lot of times I think they intentionally pick these sample inputs to try and not reveal that. They want you to actually do your own thinking, to come up with your own test cases, and to discover for yourself that even though a certain situation wasn't directly presented, it's told you very directly in the instructions that the cows are numbered 1 through n. So if you have a cow that's a negative number, you haven't accomplished that. And even though the sample input here, which is quite simple, didn't reveal that situation, that's something that if you start playing around and coming up with your own examples, you will see that happen. So it's always good to come up with your own sample data just to kind of practice the problem. Anyway, so yeah, so just kind of recapping, get your original numbers, for loop to run through each of the possible starting values. Everything's deterministic. Add things to a set or some sort of a structure to make sure we don't have any repetition. Make sure the numbers are not 0 or negative or too large. And then the first solution you find is going to be the lexicographically smallest solution. All right, that's the algorithm. Good luck coding it, and I'll talk to you on the next one.